Thank you very much for your introduction, and thank you for having me here. So it's my pleasure to share some thoughts and to discuss some of the work we are currently doing in the lab at the interface between organic chemistry and chemical engineering, in the sense that we develop processes. So the title of this talk is rather general, and I will actually cover the various topics of interest that we are currently working on in the lab, with the emphasis of one specific topic, which is what we call the transition from petro-based to bio-based chemical industry, which is maybe a bit too ambitious as a title or as a topic of interest, because what I'm going to show here is only some thoughts as an organic chemist trying to advance the chemical field and finding solutions and options for the future. So I'm going to briefly describe my general activities and research interests and give you a little bit of information regarding my lab before I jump into the main topic of this talk. So as Zacharias said, my lab was created in 2013, so 7 years ago. And when I decided to create that activity, fundamental and applied research is really my main drive for now, more than 7 years. The group is still rather small, so we are 15 people, and we are investing a lot of research efforts in mainly 4 topics of interest. And I would say that the common ground between these 4 topics of interest is the use of continuous flow reactors, including microfluidics or mesofluidics at the lab scale, but also larger flow reactors for pilot applications and further commercial scale applications. So that's the common ground, to use flow chemistry and to exploit the main benefits in terms of process efficiency to improve the chemistry. Well, improving the chemistry is a big challenge, because there are so many different things that you could think of improving in terms of, improving a chemical process. It can be, for instance, the safety. It can be the quality of the material, the homogeneity of the quality of the material you're producing, the overall footprint, the toxicity or the environmental footprint of the chemicals that you're using, etc. So with that being said, what we do is to use these assets of flow technology for providing safer processes or more refined processes in 4 main topics of interest. The first one, which is actually the most important in terms of workforce in the lab, deals with the manufacturing of APIs. So these are basically active pharmaceuticals. The second one deals with the transformation, what we call actually upgrading of bio-based chemicals into value-added chemicals. And sometimes we are actually connecting these 2 topics of interest and feeding processes for making APIs with only bio-based chemicals. And there are 2 smaller topics of interest, not because they're less interesting, but because they are more specific. The first one deals with the neutralization, the chemical neutralization of chemical warfare agents, and the last one deals with the preparation of nanoparticles. So I'm going to give you a very, very brief overview of each of these topics in a second. So as I said, I'm an organic chemist by training, but through my various postdoctoral experiences, I had the chance to work a lot with chemical engineers and to, somehow revise my way of thinking chemistry. Most standard, I would say, organic chemists would think of chemistry in terms of batch processing, while there are other options to make this chemistry much more reliable and to improve its efficiency. And that's basically flow technology and fluidics in the large sense. So in the group, we are still mainly organic chemists, although we also have process engineers and chemical engineers, and we combine forces to tackle with these problems, these issues with chemical processes. So basically, we see a chemical process as a hazard, as something that can always go wrong, even though, in the first instance, it should only produce value-added chemicals. And we try to refine the approach in designing these chemical processes to make them safer, but also to make them more environmentally friendly. And as Zacharias also mentioned, since 2017, my lab became the first European Corning qualified lab. So Corning is a manufacturer of glass products, but also plastic products, but mostly famous for glass products, including glass for constructions, screens, etc. But also they have a division entirely dedicated to reactor technology. And my work with them, it's a collaboration that actually lasts for more than 15 years now, came to this creation of this qualified laboratory here in Liège. So basically what it means is that we had enough know-how and experience with their reactors to somehow become a platform for transferring that know-how to industry. So what we do is basically train, we organize demos, but we also do on-demand process development for industrial partners. And that's a significant asset for the lab because it brings a connection to the real life, and it brings this connection to industry that is, well, unfortunately, often missing in regular organic chemistry academic labs. So you can see here some of the work we do or the services that we offer. And well, if you need to have more information, you can also check my website or directly contact me. So in the lab, as I said, we work with very fundamental approaches, but always with the aim at going to further commercial scales. And we cover different skills. We typically start with very tiny amounts of chemicals just to pre-optimize processes or just to screen different types of conditions while having a very low consumption of chemicals. So we start with what typically people would name microfluidics. And then we progressively transition during the course of a project to larger scales, mesofluidics, lab scale, mesofluidic but larger reactors, still lab scale, and then we transition up to pilot scale. So what you see here on the bottom part of this slide are two of Corning's advanced flow reactors. This one is more for lab applications, as I mentioned, and this one is more already for production or pre-production skills. Typically, they call it a pilot scale reactor. Just to give you an idea of the productivities, if you're not familiar with these reactors, with a microfluidic chip, you could, produce a few 100 milligrams per day. It just a very, very rough numbers here. In some cases it's lower. In other cases it might be higher. It depends on the concentration of the feed solution you're using. With these types of reactors, coil reactors made of PFA, for instance, you can aim at a few 100 grams per day in the best case scenario. And here and there you are ranging from, let's say, 10 milliliters per minute up to 250 milliliters per minute. So this reactor here is actually the size of a regular fume hood, excluding all the auxiliaries, the pumps and the cryostat, etc. So it's rather compact, yet capable of achieving up to 90 tons per year of production. So reduction in size, but it also comes with various assets that we organic chemists can use to improve chemistry and to make it safer. I'm just going to now move very quickly through a few examples that are not strictly related to what my intention was to discuss today in terms of transition from bio-based chemicals to from petro-based to bio-based chemicals. So these are just examples related to the other topics of interest in the lab. The first one, just to give you a quick glimpse at a few projects that we developed in the area of manufacturing pharmaceuticals. As organic chemist, I keep this very strong connection with the dream every organic chemist, has had at least once in his life, which is to have a very versatile setup that you could use to produce libraries of compounds, typically just by changing the nature of some of the chemicals that you're using, but keeping all the rest the same. So we construct flexible setups that are able to produce libraries, small libraries, but still libraries of pharmaceuticals that are, structurally related. So for instance here, that was one of the first example of connecting bio-based materials. So this is actually bio-based epichlorohydrin that we produced upstream from glycerol. I will have a chance to discuss this later on, to connect then bio-based materials to high-value added APIs. Or this is another example where we developed a flexible modulable setup to produce ketamine and ketamine intermediates or derivatives. So these are, or ketamine actually is, a pharmaceutical that is now used to treat severe depression. It's quite recent actually that it was approved by the FDA to treat severe depression, I think a year or two or so. And what we typically do when we start working on these modulable setups is to start developing the chemistry in microfluidic setups, typically made of PFA coils to keep the cost very low, but also to favor the transfer of the know-how, because I think, and that's something I learned from MIT actually, it's kind of counterintuitive, because you would think that at MIT they have a lot of money, so they will not care about buying fancy, costly equipment, engineering stuff, etc. But actually, they're not into that. They're more into the fact that if you can build it yourself with low tech, widely available, like for instance, PFA or HPLC connectors, if you can build it yourself, because you know exactly how it works, then the chance that this technology would penetrate the further generations of chemists is actually higher than if you would have to only work with very expensive material that only a few can afford buying. And that's how I started working here, trying to do with very common equipment in the lab some advanced flow setups to make libraries of compounds, and in some instances, very active psychotropes or very active, like steroids, APIs. We started at lab scale, and then we transitioned progressively to commercial scale. So for instance, for ketamine, we went up to a few kilograms per day of this pharmaceutical, which is obviously a lot for a psychotrope like ketamine. Well, another topic of interest that I'm not going to discuss a lot here, although it's also an interesting illustration of how green chemistry or sustainable process development can also have an impact on something like chemical neutralization of chemical warfare agents. So we worked with a team of computational chemists, organic chemists, and also chemical engineers to develop these very compact setups to neutralize, chemically neutralize, chemical warfare agent, well, actually simulants of chemical warfare agents, because we have no military clearance to work on these kind of compounds, but to work on compounds that are close enough to be good mimics of these chemical warfares. And what we ended up developing was a very compact setup that would only use light and air to neutralize chemical warfare agents. And then the last topic before I jump into this bio-based chemistry or bio-based chemicals deals with nanoparticles, because we also can tailor the size and the properties of nanoparticles, like for instance gold nanoparticles, and we can do that very, very accurately under flow conditions. So we started having this interest on gold nanoparticles for their catalytic applications, and we developed a photochemical process that was actually tested up to the commercial scale in a very large flow reactor a few months ago. But now I'd like to jump into the main topic of my talk now, which is the upgrading of bio-based chemicals to high value added chemicals. Can be pharmaceuticals, but can also be monomers or green solvents or other, I would say, industrially relevant building blocks. And again, we have an approach that is very different from standard organic chemistry. So we will look at a process and we will try to bring the assets of flow chemistry to that specific chemical transformation, and then we will validate the ideas we have in the lab to further implement it to the pilot scale. And in some cases, through the network we have of industrial partners, we can go even further than just pilot scale. So I'm just going to give you a little bit of context on this, upgrading of bio-based chemicals. I'm not advocating in any sense the use of bio-based chemicals, and I'm not against petro-based chemistry. As an organic chemist, I'm well aware of the value in the actual context of using petro-based chemicals, but I'm also looking at the future and seeing opportunities to already start building know-how, so that in the future we will be able to convert bio-based chemicals and to feed the actual processes that do exist, but that are currently based on petro-based chemicals. So 95% roughly of the chemicals we use are organic chemicals that are sourced from petroleum and natural gas. And if you do the math, I think it's very quick to do this math. These are non-renewable resources that come from finite reservoirs. And as the previous speaker nicely illustrated and said several times, people keep saying that, at least 10 years ago, that we will run out of petroleum in, let's say, a decade. And now, well, with new technologies, you can find different or new reservoirs of gas or petroleum, and it seems that it's a never-ending story. But there is a fact, and regardless of new drilling technologies or new extraction technologies, these are finite reservoirs. So at some point, with the increasing numbers of humans, you can see here by 2050, 9.7 billion humans, that's the UN forecast, the population will keep increasing. And if we want to sustain or even further improve our living standards, we will still have to run industry and to source the building blocks that we need to produce chemicals. That can be pharmaceuticals, cosmetics, fuels, or whatever else we need to sustain our living standards. We will have to source them from somewhere. And one possible option would be to source them from renewables, so-called bio-based chemicals or bio-based resources. Now, the problem with these bio-based chemicals, as we will discuss it in a few seconds, is that they are very different from the typical building blocks that we used to work with from petroleum. Well, you can directly see on this cartoon here that typically they have a very high oxygen content, while petrol-based chemical building blocks well, they're lacking oxygen. They're basically solely made of carbon and hydrogen. So that's already a major difference. Now, if you're not a chemist, it might not mean anything, but if you're a chemist, it means a lot, because it means that the processes that you will have to implement to convert these building blocks into something that you can use actually to feed what exists, not to, have to start again from scratch. Well, the first step would be to remove that excess of oxygen from these bio-based compounds to recover something that we are more familiar with. So, and as a chemist, well, it's very challenging to break these carbon-oxygen bound, because typically this would require high temperatures or very harsh conditions or fancy catalysts. And these bio-based chemicals are very sensitive to temperature, especially temperature, and they will very rapidly decompose. So, well, just to give you more details about where we actually are in terms of process development, we are actually in the lab somewhere at this stage. So we use these small building blocks that are derived from biomass, and we try to upgrade their value. So basically we do transformations, we develop processes to transform these compounds into compounds with a significant increase in their value. And there are other groups that are actually more into the conversion of biomass into bio-based macromolecules, and other groups that are into converting these bio-based macromolecules into these small building blocks. That's not our job, that's not our core expertise. We are at the very downstream part of this whole scheme. So you see these very small molecules, it's only a selection of some molecules that you could actually produce from these bio-based macromolecules. And these are called bio-based platforms. So the term platform is actually related to their inherent chemical potential, in the sense that starting from ethylene glycol, for instance, which is a very small molecule, you can produce a wide diversity, a library if you want. If I have to use specific wording from organic chemistry, these would be versatile building blocks. You could actually do a lot of different things of interest for making polymers, fuels, pharmaceuticals from these small building blocks that come from biomass. Actually, well, there is a list of the most promising platform molecules. The list is actually a little bit outdated. It dates from 2004. It was actually updated 10 years ago, but basically you have the summary of the list here. Well, the different structures doesn't really matter. What really matters is, like, you can see from these compounds that polyols, so molecules bearing several hydroxyl groups, represent actually a large portion of this list of bio-based chemicals. And, well, that's one of the reasons why we started working on polyols and why we started trying to develop processes for upgrading bio-based polyols into value-added chemicals. So I made a selection of some processes that we developed for upgrading polyols. So you see, transitioning from petro-based to bio-based chemical industry comes with strength, but also challenges or weaknesses. And so far, the main weakness is that these processes, well, it's kind of counterintuitive. They are non-atom economic, so they would produce a lot of waste. They would consume a lot of energy, and basically overall they are expensive, much more expensive than petro-based processes and all the processes that use petrol resources. And as I explained, because they are the bio-based platform molecules are so different in terms of structure and properties from the petrol-based platform molecules, you need to develop and you need to implement new technologies or new upstream processes to transform them into value-added chemicals. And as flow chemists, well, we believe that combining the assets of flow in terms of heat exchange, mixing efficiency, overall reduction of the footprint could be a potential option for bringing, the upgrading of bio-based chemicals from a purely academic interest to something that has a future in industry. So for most of these projects, we work with Corning as a supplier of the reactor, and we had a chance to transpose most of the work that was done on the lab scale to at least a pilot scale. So I gathered here a selection of 3 main processes that we developed on polyols, and they are gathered according to the main reaction or the main technology that was used for their transformation. So I'm going to discuss shortly what is named the deoxydehydration reaction, so in short, the DODH reaction, which is basically a way to transform a vicinal diol into olefins. So basically to remove 2 hydroxyl groups from a carbon-rich, oxygen-rich backbone to make an olefin. And then I'm going to discuss also some examples on the carbonation of polyols, which is actually not a reaction that we use to remove oxygen from a polyol, but we will mask or transform a diol into a cyclic carbonate. And you will see that in the corresponding section that these carbonates, they have a high value for industry as solvents or as for monomer for making innovative polymeric architectures. And the last section is a revisit of known industrial processes from Solvay and Dow to transform polyols. In this example here, glycerol only, but we are working on higher polyols now with the same technology to convert these polyols into oxiranes, epoxides. And these epoxides, which are very reactive molecules, can be used for making active pharmaceuticals or polymeric materials. So I'm going to start with the DODH, so the deoxydehydration reaction, which was summarized in this scheme here. So you start with a polyol bearing a vicinal diol function, and if you add the appropriate combination of reactants, so typically reductant, additives, or a metal catalyst, well, you could remove these 2 hydroxyl groups and get this olefin plus side materials. And there are typically 2 main strategies for making this DODH reaction. You could either rely on stoichiometric additives, and you have a diversity of reactions that are using stoichiometric additives to trigger this reaction, or you can actually work with catalysts, mainly rhenium, molybdenum, and vanadium, to do the trick. But you need also to add, which is actually a bit counterintuitive with this catalyst reaction, catalytic reaction, you need also to rely on a lot of stoichiometric additives to make it work. So I became interested in this reaction here, which is actually an old school reaction from I think the 50s, the early 50s. It's called the Eastwood reaction. And the Eastwood reaction is, well, you have different variation on the same reaction, but basically you start from a polyol, like a vicinal diol, and you would mix it with either formic acid or triethyl orthoformate or a combination of both. You will heat it up, and that will trigger this deoxydehydration reaction. It will release CO2, water, and ethanol. So Of course, I understand that some of you will have remarks on the fact that we are releasing CO2. It doesn't look like a very bio-based process or sustainable process because you're releasing CO2, but I understand that, but you have to think all the things into consideration here. The main aspect of this research is to convert these polyols into olefins, not to reduce the amount of CO2 that is produced. It's another area of research that we are dealing with. And if you take a list of the many different vicinal polyols, or vicinal diols, or polyols that you can find in biomass, and if you apply this DODH reaction, so you have the list here of different types of polyols, and the next row, the next column is actually the products that you can get from this bio-based starting material by applying this DODH reaction. And it's really interesting to see that from bio-based polyols that are, for the case of glycerol, considered as waste from some specific industries like the biodiesel industry or the oil food grade industry, glycerol is just a waste. Well, from glycerol, you can actually access allyl alcohol and further acrolein or acrylic acid that are really staple building blocks in the polymer industry. And from sugars like erythritol, well, you can access butadiene or furan derivatives or other olefinic compounds that have a very high value nowadays on the market. And you can do the same analysis on other sugars and other polyol derivatives. And you can see that actually you can reach a wide variety of compounds that are traditionally petro-based. So with glycerol, because most of the things I'm going to discuss now relate to glycerol. Glycerol is a very complex molecule to work with, not because of the chemical complexity. It's a rather simple molecule if you look at it. It's only 3 carbons and 3 hydroxyl groups, but because of the viscosity of glycerol. So it's very difficult to pump, to handle glycerol, especially in flow. But what is also very difficult with glycerol, which is maybe something common with all bio-based materials, is that the quality of the starting material really depends on where it comes from, how it has been produced. And believe me, for glycerol, crude glycerol is extremely complex to work with because you have so many different impurities in that glycerol, in that raw glycerol. And that's another aspect of this research dealing with bio-based materials. Most of the development that are reported in the literature are actually being done on refined materials, so purified glycerol, for instance, or purified polyols. And very much less is said about what happens when you use raw material. And especially for glycerol, we made some tests for different reactions that we developed on glycerol to make sure that actually what we developed in the lab on refined glycerol was also applicable to unrefined raw material. And of course, you always have major surprises and major differences. So you see, when we do start a new project, we like to implement a wish list or a to-do list of what we have to achieve and what we have to meet as milestones. So when you think of the DODH reaction, one of the easiest model to work with to start implementing this reaction is glycerol, because it's the simplest polyol that you can get from bio-based materials. The process itself had to solve the major issues of handling glycerol, not by adding chemicals that are not used for the process, but ideally adding chemicals that would help processing glycerol, but that will still be used for the DODH reaction. And then it would have to be compatible with unrefined material, implement also inline analysis and downstream processing, and then ideally Again, this old dream of an organic chemist, if it works for one polyol, it should also work for different types of polyol, and you would get libraries of olefins on demand, depending on the polyol that you start with and depending on the conditions you're applying to that polyol, but keeping more or less the same setup. So when we started working on this, we took two different polyols as models, glycerol, the simplest one, and then the erythritol, which is like one carbon and one hydroxyl group more than glycerol. And if you look at this, but just by adding one carbon and one hydroxyl group, you get diversity. So one carbon and one hydroxyl group will get you more possibilities applying this DODH technology to access different types of olefins. So of course it doesn't really make sense to produce butadiene from erythritol, because butadiene is like maybe 100 times less expensive than erythritol current market prices, because butadiene is mostly petro-based. But for this 3,4-butene diol, it's much more interesting because this compound is much more expensive than erythritol currently on the market. And you can use it to further valorize these two remaining alcohol groups here to make carbonates and to enter polymers. I will discuss this in a few minutes. So you see, going back to glycerol, I mentioned that glycerol was a very difficult bio-based polyol to work with from very practical aspects relating to the viscosity of glycerol. So what we started developing was a reaction. So that's back to very fundamental approaches, which is the basis actually of this Eastwood olefination reaction, which is to trigger dynamic covalent exchanges that forms different intermediates. The viscosity of those are drastically reduced. So you mixed glycerol with triethyl orthoformate in the presence of formic acid, you would form mixtures of dioxane and dioxylane intermediates. You would also release ethanol, and these equilibrium will actually decrease the viscosity of the reaction mixture. And that comes with a very practical asset, because now you have a solution that you can pump because it has the viscosity of ethanol. So it's very easy to pump, and you solve the issue with the high viscosity of glycerol. And once you have these compounds, it's not like I'm adding chemicals just to reduce the viscosity. I'm adding chemicals that will reduce the viscosity, but that will also trigger that DODH reaction, so that olefination reaction. I'm just going to give you a quick glimpse here at the process on erythritol. The downside of working with higher carbohydrates, like for instance erythritol, is that it's not liquid anymore. Glycerol is liquid, it's viscous, you have to handle the viscosity, but at least it's viscous, so you can pump it or find a way to pump it. Erythritol is a solid, and it decomposes when it melts, so it's impossible to handle it as a liquid unless you work with a solvent. And as you probably know, solvents are the #1 responsible for waste production in chemical processes. So it's a problem, but there are, not so many options to circumvent that problem of using a solvent. Well, you know also that there are solvent guide lists that you can use to decide whether the solvent that you think would work for your chemistry is also acceptable for environmental aspects of the solvent or industrial aspects of the solvent. And so we found out that DMSO, which is actually listed as a problematic solvent, not a non-recommended, it's problematic. So it's in between, it's actually tagged as a yellow or orange solvent, not a green or not a red one. But the reaction requires a very polar medium to work. and DMSO actually help this DODH reaction. And if you do this DODH reaction, you can tune the issue of the reaction, the output of the reaction towards this olefin. And if you increase the amount of the additives you add, you will form mostly butadiene. So in the concept of having something that is modular and that will help you to produce libraries of compounds, starting from the same starting material or adding different types of additives or changing the parameters of the reactor setup. It is a very interesting application here, an illustration that depending on the conditions, you get one compound or another olefin with very different industrial applications. And if you change the reaction medium, so going from DMSO, which is a very regular FDA-approved solvent, to ionic liquids, you get a very different output with different compounds, different applications. Again, what I wanted to illustrate here is the diversity or this concept of making libraries of compounds, starting from one starting material, using the same setup, but applying different conditions. And our interest was triggered by this compound, 3-butene-1,2-diol, which is actually worth 100 times the value of erythritol. So it's typically petro-based, and this was the first application or the first illustration of a bio-based process for making this olefinic diol. And I will keep building up on this olefinic diol in the next section to show you some of the work on the carbonation of polyols, but I will also keep working on glycerol. As I explained, glycerol is like a model for developing processes on bio-based polyols. What I'm going to shortly discuss here relates to carbonates, and more specifically cyclic carbonates. So these cyclic carbonates, they have applications ranging from cosmetic preparations or pharmaceutical preparations to solvents and polymers, so wide-ranging applications. And there are mainly two main routes to access these carbonates. This route here works with carbon dioxide and epoxides, but you know, it has pros because it uses carbon dioxide, but it also has cons because it works with epoxides that are toxic and volatile and sometimes unstable. And on the other hand, you have another strategy that works with vicinal diols. So, for instance, polyols, bio-based polyols, and a carbonation reagent that is activated, so that is not stable as carbon monoxide. And what we are developing in the group here is dealing with carbonation procedures that work with either urea or a very well-modeled and very well-known carbonation reagent with it, which is dimethyl carbonate. And we had two targets at the beginning for a cyclic carbonate. So this is a molecule named vinyl ethynyl carbonate, which is actually a carbonate that you can access from the diol that I just presented the synthesis of, starting from erythritol. And the other one is a rather simple carbonate, which is glycerol carbonate, directly derived from glycerol. And both have applications in industry. So as I mentioned, there are different types of carbonation reagents that you can use, but in the lab we work mainly with urea and dimethyl carbonate. What I'm going to illustrate relates mostly to dimethyl carbonate, which is a very well-described carbonation reagents. And you can use different types of catalysts, either organic or inorganic catalysts, to trigger the carbonation of diols. In the lab, we typically work with organic catalysis rather than inorganic catalysts because that's our core business. So what you will see in the next slides relates to mostly organocatalysis, either heterogeneous or homogeneous organocatalysis. So to make a story short, because it was actually based on a long standing effort of finding the best organocatalyst and the best conditions to avoid decomposition of the starting materials, we ended up developing two competitive processes with both assets and disadvantages. An homogeneous process relying on an organic base, in this example DBU, which is a known catalysis for this reaction, but we went further on the optimization of this catalyst. And basically you see here the setup is very straightforward. You have two inlets, so two feed solutions, and you pump these two feed solutions in a microfluidic or a mesofluidic setup, depending on the scale you're working on. You speed up the process with two leverages, I would say. First one is a higher temperature than the usual, and the second one is playing with a very high mixing efficiency, since most of these feed solutions are not miscible. And then you get a very quick reaction time, 4 minutes at 160 degrees C, where you get this high value added carbonate with a very high conversion and very good selectivity. And then this is the heterogeneous version, which is on the paper appealing in the sense that it's heterogeneous, in the sense that your catalyst has been heterogenized. So it's fixed, it's anchored on a support in a packed bed column. So the difference with the homogeneous process is that it should simplify the downstream processing, because for the homogeneous process, well, everything goes with the flow, and in the end, your final product gets contaminated with the catalyst, and you have to implement heavy downstream purifications to try to remove that catalyst, which is, costly, workforce and time consuming. So it's sometimes easier to implement, but then on the downside, you have to work a lot on the downstream purification. While the heterogeneous process has the advantage of having this catalyst anchored on a solid support in a column, and you flow your chemical through that column. And if the catalyst is not released, does not leach during operation, well, it should not contaminate the final product. But you have the downside also of heterogeneous catalysis, which is typically that it will work for a while, and then it will start decreasing in terms of efficiency and selectivity. And you have to regenerate the catalyst or to change the column. Typically for organocatalysts, we do not regenerate, we change the column, we change the active catalyst species. And increasing the complexity, and we came up with this concatenated process where basically you're adding steps and connect all the modules in series to have something that is fully streamlined from A to Z, A being the starting material, Z being the final product. And while starting from a bio-based polyol, erythritol here, you can apply first a DODH so that you get an olefin still bearing this vicinal diol here. And in second instance, you can do the carbonation of this diol to get the final carbonate, which is here a very high value added compound. What we also try to do is to implement inline analysis to not only accelerate the optimization at the development stage, because you really have eyes inside the reactor, so you know exactly what kind of parameters will increase the selectivity or the conversion. But then later on, we also use inline analysis for quality control when we transition to larger scale. So we just have an example here that combines IR, these are the orange dots, and that's basically inline analysis or online analysis. So the IR spectrometer reads continuously what leaves the reactor. But you also have the blue dots, and these are offline GC analysis, and we typically combine both in and offline analysis to have something really robust, because typically inline analysis will be more qualitative, while offline analysis would typically be more quantitative. So as I mentioned, we did work also on the optimization of the organocatalysts, and well, going back to my background as an organic chemist, what an organic chemist likes to do is to have scopes and large tables with a variety of catalysts and to try to pick up the best one. So that's basically what you see here. These are a range of organocatalysts, so these are named super bases, super organic bases. And you can see that most of them performed quite well for this specific carbonation of glycerol, but Barton's base, so this guanidine, was one of the best in terms of both conversion and selectivity, plus the cost, because the cost is also something to be considered while developing such processes. So that's why all these fancy bases here that are called phosphazines, they are all very potent for this reaction, but they are so expensive that would simply kill the interest of the process. And again, once you have a functional device that produces an optimized base to catalyze the reaction, what you want to do, as at least in my point of view as an organic chemist, is to see how versatile the reaction or the process is. And you see here that's typically the library generator that we like to play with. You have a setup, you have functional conditions, robust conditions. You would just change one of the feed and see how it proceeds. And in this case, rather than using glycerol, you change the nature of the polyol and you start producing different types of cyclic carbonates. And in this sense, it is a very versatile and very modulable process that leads to libraries of compounds of interest. We were also able to bring that into a pilot scale because we succeeded in the transposition of this process to a 10 kilogram per day scale for glycerol carbonate. Yet, the main criticism was the cost of the catalyst. Even though this is not a very expensive organocatalyst, it is still very expensive. So we did further optimizations, and one of my PhD students came up with this ammonium bromide, or he screened a wide variety of ammonium salts, and this ammonium bromide, which is a very, very common reagent in organic chemistry labs as a phase transfer catalyst, for instance, is very cheap, yet also very efficient for this reaction. The temperature is maybe a little bit higher than for the other organic super bases. It's 180. For the organic super bases, it was ranging from 120 to 160, so it's a little bit higher, but the cost of the catalyst is so low that the process becomes really interesting. You see the conversion and the selectivity, and you see here that the process was also validated on pilot scale, but also using crude glycerine. So crude glycerine contains water, methanol, sulfates, different types of salts depending on where it comes from. Of course, it affects the performance of the reaction. You can see a drastic drop in conversion, yet you still have conversion and you have a very high selectivity for glycerol carbonate. And if you take all of that into account, the very low cost of raw glycerine, the very low cost of the catalyst, the very high efficiency of the process, well, you get something that has a potential for further commercial applications. Now, the very last thing I'd like to illustrate is the transformation of polyols into oxiranes, so epoxides. So it's a known process. There is nothing really new here regarding the chemistry. It's new. It's new from, I would say, the perspectives or the concepts that were developed based on these reactions. So these two epoxides, this is epichlorohydrin. and this is glycerol. They are typically synthesized on the industrial scale from propene, so a very common petrol-based chemical. But two major industrial players, namely Solvay and Dow, they have also developed processes starting from glycerol. It combines two steps, a hydrochlorination using hydrochloric acid, and then a dechlorination step using sodium hydroxide that can also provide epichlorohydrin or glycerol from this time bio-based glycerol and not from propene. So we revisited some of this reaction and we developed a flow process. We optimized the catalyst and then we went further on seeing if it was possible to use these epoxides for making value-added transformations towards pharmaceuticals. So again, as typical with my research programs, we have a wish list or a to-do list. And it typically decomposes the reaction scheme into steps, like unitary operation steps, like single reactions, step by step, and all the criterion that we have in mind to have a successful development. So for instance, step one is, even though it contains different chemical steps, is the transformation of glycerol into either epichlorohydrin or glycerol. If not selective, can we also separate these two compounds to use them? And then what can we do with them? Can we transform them into value-added chemicals? So the reaction with glycerol, the first step of the transformation of glycerol into epichlorohydrin and glycerol is the reaction with hydrochloric acid. So it's an interesting reaction from the practical aspects because you're working with aqueous hydrochloric acid, which is not expensive, but it's fairly challenging to pump it. Not because it's viscous, but because it's so aggressive for the main types of common pumps we have in the lab. And on the other side, you can work with neat glycerol, and we have also validated this process on raw glycerine. So it's very simple from the conceptual aspects of the process, but in practice you have some major challenges related to the corrosion of HCl and the viscosity of glycerol. So the reaction also requires a catalyst. Acetic acid is a very well-known catalyst, so we started with acetic acid as a model, and you can see that the reaction typically takes up to 30 minutes, up to 150 degrees C, and it gets you a variety of chlorinated compounds that you can further use for the second step of the reaction. So the best conditions were here highlighted in gray, 20 minutes, 140 degrees C, and then you have accumulated yield of 88% of all of these three chlorohydrins. So this trichloropropane compound was never observed in the trials we made. And once you're here, well, you can either start working on the second step, or you can actually try to optimize the selectivity between these monochlorohydrins or these dichlorohydrins that you formed during the process, because the amount of each of these chlorinated compounds will have an impact on the ratio between the two epoxides that you can form during the second step. And so we did again some screening of different carboxylic acids as catalysts, and we found out that pimelic acid, which is this dicarboxylic acid, is actually one of the best catalysts for this reaction, and it gives a very high and very unprecedented selectivity towards this chlorohydrin. That is actually the best case scenario if you want to have a high productivity in epichlorohydrin. And once you're there, well, the second step is actually very easy to implement. Using sodium hydroxide, the reaction is super quick. super quick. I've seen faster reaction than this, but it's typically done between 1 and 10 minutes of reaction time at 20 degrees C. It's very, very important here to control the exothermicity, because you're not only neutralizing the excess of hydrochloric acid, but you're also triggering this epoxidation reaction. But the most novel part of the work was downstream the process, where we developed a selective extraction procedure downstream the reactor to selectively extract glycerol in water that would provide a usable stream of glycerol in water, and of epichlorohydrin in an organic solvent. And the best one for the extraction was actually methyl tertiary-butyl ether. From very practical aspects like the low boiling point to concentrate the solution, the non-miscibility in water, and the more or less low toxicity level of this solvent. And once we were there, where the extraction were selective, the only remaining part of the project was to be able to use this epoxide to make different types of pharmaceuticals. I'm not going into the details of the preparation of these different pharmaceuticals, but you can see here the motif, the pattern of this epichlorohydrin, and in blue in the different APIs you can see where all the carbon atoms and the oxygen are. We were also able to scale this process to a 5 to 10 kilogram per day, depending on the target, with silicon carbide reactors from Corning. So I think it's time for me to wrap this up. Well, I haven't really insisted on the chemical engineering aspects of flow chemistry, but as an organic chemist, I see it as an opportunity to redefine and to revisit chemistry, and especially in the context of transitioning from petro-based to more bio-based resources. I think this really opens up new possibilities and new perspectives for developing processes, not only at the lab scale, but also at the commercial scale. Thank you.
Well, thank you very much, Jean-Christophe. It's a beautiful talk, beautiful work, and very impressive work as well on the scale up and all the revisiting of this dehydration, cyclization, and so on. So just have a look at the chat. So please, people, you're free to ask questions on the chat. The questions are open. Session for questions is open. I will start basically very, very briefly to start the discussion. Just at the end, you mentioned you didn't go into details of the practical aspects of flow chemistry. Have you seen in your mainly in the chlorination reaction, for example, if you can improve the selectivity with the residence time, or is this depending on the residence time? Can you improve the selectivity compared to batch process? Can you tell us a little bit more about that?
Well, sure. I think it's not what really matters for the selectivity in this very specific reaction is more the catalyst than the process technology itself. And the practical aspect as well, because you see in batch, acetic acid is the reference as a catalyst for this chlorination reaction. But it's well known that in large batch reactors, acetic acid will actually evaporate because of the high temperature. And then you would lose the catalyst and the efficiency of the reaction would drop over time. And transposing this reaction, known reaction, with a known catalyst, acetic acid, to flow would simply solve that issue of having the catalyst evaporating, because in flow everything would be contained and sealed. So I would say that that's the main difference. The selectivity is more influenced by the nature of the catalyst, and you can afford to play with more intense conditions or intensified conditions like higher temperature in flow than you would in batch. But it brings another aspect than just selectivity. So I would not say that transposing from batch to flow will affect the selectivity. It's more that transposing to flow would open up new possibilities in terms of process windows, and you would be able to access higher temperatures while not losing your catalyst for this specific reaction.
Okay, thank you very much. I do agree, as also working in flow chemistry, that you're not often changing the selectivity, but moving opening to the different processing windows is very interesting. As an organic chemist, I also have an organic chemistry question. Why do you need, you're mixing the acids? So you have you say you have a carboxylic catalyst, acid catalyst, and HCl. Actually, I did not really understand how HCl is coming into the reaction. Could you re-explain maybe a little bit how you introduce hydrochloric acid? Yes, exactly. I think you're muted. I don't know why.
Sorry, is that better?
Yeah, that's better. Yeah.
Excellent. So you're basically using aqueous or hydrochloric acid. What you needed to introduce the chlorine atoms here. And if you're not introducing a carboxylic acid as a catalyst, the reaction simply doesn't work, or you would require very long reaction times. So the most commonly accepted mechanism is that you have a transesterification first, and then the transesterification will actually lead to the formation of an oxonium intermediate. And that oxonium intermediate would then eventually react with chlorine anions that would form the different forms of hydrochlorogens here.
Okay, that's very nice reaction indeed. And how do you introduce this? Because on the slide it looks like there is a sort of
yes, it's a sampling loop.
It's a sample loop, all right, I guess.
Yes. So this is the lab scale production scheme that we use. So to avoid destroying the HPLC pumps we have for handling liquids on the lab scale, what we ended up was simply to work with 6-way valves and a sampling loop. And we would load the sampling loop with concentrated hydrochloric acid and push it with water out of the sampling loop to the reactor. So obviously, this is not something that would function for large-scale production because you're limited by the volume of the sampling loop. Mm-hmm. But then for the production scale trials, we had PTFA pumps that we could use directly on HCl.
Okay. I guess also on large scale you can use other types of pumps that are more efficient or more go to higher flow rates, but also still made of PTFE tubing.
Yes, absolutely.
Well, I'm just going to have a look at the chat because I think people have some question. First question is from Christophe Len on slide 28. What is the real interest to flow at 11 bars? So I can't recall exactly, but slide 28, yes.
The real interest is that actually you're releasing methanol as a side product of the reaction. And at 180 degrees C, well, it's a gas, so you need to increase the pressure to keep it liquid. So it's a really practical aspect of keeping everything liquid to control the residence time.
Okay, then we have a question from Meng Shui Zhang. She's interested in to get a glimpse of your vision of downstream processing in flow chemistry, as this might be one of the weaknesses of flow chemistry. You introduced an extraction on your last example. Is it a homemade system or perhaps it's a Zyput?
Yeah, so most of the time we rely on Zaput. So I'm not going to lie. I had a chance to work at the very beginning of Zaput when I was a postdoc at MIT. So I really adopted these Zaput membrane separators for downstream operation. So they are very unique tools. And of course, they will open up some options for downstream processing, but it's not universal in the sense that in some cases, well, you don't have to rely only on membrane separation or liquid-liquid or gas-liquid separation for downstream operation. So I agree with you. In the actual state of the art in flow chemistry, a downstream processing or intermediate processing between steps is still a weak point, or there's still a lot of room for developing new tools or developing new technologies. Because so far, as I mentioned, if you're looking at what is reliable and what is available on the market for downstream operation, you have Zaput, and that's basically it for such volumes and such flow rates for liquid-liquid extractions. If you need to remove some specific, like the catalyst, if you have catalyst leaching, or if you're using homogeneous catalysis, you can always work with ion exchange resins, but they also have limitations and weak points. And it's fairly difficult to have, with this concept of flow chemistry, so within the definition of micro and mesofluidics, it's fairly difficult also to have reliable distillation or other types of downstream operations truly inline and truly continuous. So I fully agree that there are still plenty of room, and that would certainly be the direction of research for the next few years ahead of us to further develop these flow technologies.
All right. You also, just to finish, you also mentioned using solids and for example, making nanoparticles. And I'm seeing a new questions. When using heterogeneous catalysts, are you looking for coated honeycomb structures from Corning? Could you comment over these catalysts?
So, yes and no. Actually, when I'm typically using a heterogeneous catalyst, I'm using a packed bed column. So I'm packing myself a column with a catalytically active material. I've been considering with Corning to have trials with coatings, catalytic coatings on the surface of the inner surface of the reactor. But that's still too early to discuss any results from there. So typically, from my perspective, when I need to use solids, I would either consider packed beds, or I would consider melting the solid if the solid is a reactant, and if the solid, is not decomposing upon melting, or using ultrasonic waves to keep the solids moving in the reactor. But I have no experience with so-called honeycomb structures.
Okay.